All right, so back to hydraulics and buoyancy. We are looking now at continuing on from the buoyant force that we found. We're going to move on to Archimedes' principle. And so, sorry, just getting the slides going. Here we go. Archimedes' principle. The buoyancy force on an object immersed in a fluid is equal to the weight of the fluid displaced by that object. So that is exactly what we found during the last video. So all of that working we did, it was whatever it was, 7 or 8 slides of discussion, of consideration, and of playing with those equations, led us to Archimedes' principle. So as I said, I could have just led with this. I could have told you Archimedes' principle, explained it, and then talked about how you arrive at it. But hopefully approaching it from that angle will reinforce the principle for you and help you remember it. Even if you forget the name of it, at least remember the idea of the principle. The classic story, of course, of how Archimedes discovered this was that he was tasked with determining whether or not a crown was made of real gold, and he couldn't melt down the crown in order to determine what it was made of, and he didn't have any reliable means of checking the volume immediately, so he couldn't necessarily determine the density of it by his standard methods at the time. And what he came up with was this idea here. If he balances the crown perfectly with a reference lump that is known to be pure gold, then that means that the two objects have the exact same mass, right? So this balance here, they are the same distance from the center point where it's hanging, so the same forces would provide equal and opposite torques. And obviously if they have the same forces, they have the same mass, because gravity is the only force acting on them. So what he did is he set up this balance, and he had the forces being equal between the crown and some other reference that he knew was pure gold from previous explorations. And then he submerged them underwater. And what he found was that one side went higher. Right. Well, actually, I don't know if he did find out if it went higher, but what he would find if it wasn't real gold, if it was something less dense than gold, is that it would go higher. Right? And now the reason for that is that as we just found out through our discussion, the volume of the object determines how much water is displaced, and how much water is displaced determines the buoyant force on the object. So remember that both of these two submerged objects have the same same weight force downwards, but the one with the larger buoyant force would therefore go upwards when it is submerged. So the net force on the crown, if it is not made of gold, will be larger than the net force on the solid lump of gold. So this, again, you might have to take a bit of time to just think this through, think about the equations. So what we're saying is if the object is made of something less dense than real gold, then it would have a larger volume to get the same mass. Right? We set them to be the same mass in the first step. And if it's got the same mass, but a larger volume, then it will have a larger buoyant force. And so if it had the same weight force but a larger buoyant force, it now has a larger net force, or smaller downwards, larger upwards, depends on whether the net force is up or down. But the buoyant force being higher means that when you submerge it, it will now raise compared to the object that it was previously balanced with in weight alone. So that's where Archimedes' principle comes from. At least that's the story that we're told behind it. And of course it works perfectly, so that is a very real sort of problem that you may be given to solve. But for now, obviously, we're going to continue on. We're going to think about the forces while it's submerged and what the magnitude of the different forces mean. So we have a buoyancy force acting upwards. We have a weight force acting downwards. Right? Do we have any other forces? I realize I've jumped ahead a slide by telling you there's a weight force, but hopefully you all agree there's a weight force. We already talked about that on the previous slide. So we've got an object underwater. It's not hanging from a thing like Archimedes' principle was. It's just an object submerged like our cube earlier. Are there any other forces? We've got the buoyant force and the weight force. Is there anything else? The only other one should be the weight force if it's just submerged and we're not holding it, not forcing it, not doing anything else to it. Right? If it's just submerged, then that's all there is. There's nothing else touching it, so there can't be any other forces. Right, so the net force in that case is the buoyant force minus the weight force. Again, it depends which way you define up or down as positive or negative. I'm going with up being positive, so the buoyant force is positive, the weight force is negative. And of course, the buoyant force, as we just saw, is equal to the weight force of the fluid displaced. So we've got F weight fluid minus F weight object. When we're dealing with buoyancy and we talk about the weight of the fluid, we often forget to add on, or just don't bother adding on, fluid displaced. We don't bother with the displaced term because it becomes a bit of a mouthful. So when I'm talking about a submerged object and I say the weight of the fluid, I mean the weight of the fluid that's been displaced by the object, but I'm not just going to say that whole sentence every time, all right? So that's just, again, a term that you'll just have to get used to, that you need to be able to interpret when we're dealing with problems. So the net force on a submerged object is known as the apparent weight. We've got the weight force downwards, a buoyant force upwards. The net force is going to be less than the actual weight because the buoyant force is always going to be opposing the actual weight. So that means the apparent weight will always be less than the actual weight, and it'll be less by an amount equal to the buoyant force. Now, I just said that I defined up as positive and down as negative, and now I've said that the weight force will usually be written with a positive value. Again, it's just terminology. When we talk about weight forces for objects, we always give positive values. If I say, what's the weight force on this 1 kilogram mass, you're going to tell me it's 9.8 newtons. You're not going to tell me it's negative 9.8 because A, we haven't defined a frame of reference yet, and B, when we talk about weight, we know that it's always straight downwards. That's what gravity does. So the same thing with apparent weight. When I ask you for the apparent weight of something, you can just give me the value. You don't have to specify negative or downwards because the term weight specifies downwards. It's a gravitational attraction. So we're moving on to thinking about the motion now. So previously we were just talking about something that was underwater at some instant. Now the question becomes, what's going to happen if we actually watch it? What does it do? Does it accelerate upwards or downwards or just sort of stay underwater? And from the net force, the apparent weight, we can see that if the net force is downwards, then we have an object that will sink. Right? Downwards force, net force down, it's going to accelerate downwards, it will sink. And similarly, if we have a net force upwards, then a positive net force, it will float. It will go up towards the surface of the liquid, of the fluid. So that's floating and sinking. All it means is that the net force, or the apparent weight, is positive or negative. So an apparent weight downwards is going to give you a sinking object, and an apparent weight upwards is going to give you a floating object. Now, we talk about apparent weight, and I just said you don't have to worry about positive or negative, and now I've just said that a negative apparent weight is down and a positive apparent weight is upwards. And the point there is that we don't actually deal with negative apparent weights or positive in the floating sense, because an apparent weight is the weight of something when it is submerged, and if something is submerged, then it can't be a floating object unless we're pushing it down. But either way, it's not just sitting underwater. Yes, confusing, but you'll just have to manage the best you can. What about those floating objects? When it is partially submerged, how do we deal with that? So we've got an amount of fluid displaced that is now less than the object itself, the object's volume. This grey cube is floating in this big body of fluid. I've just drawn a chunk of it, but it's a big body of fluid. It could be a pool or a lake or whatever. And we've got this grey cube floating in it. How much fluid has this grey cube displaced? Well, it's not equal to the volume of the cube. Right? It's less than the volume of the cube because some of the cube is poking up out the top. What does that tell us? Well, it tells us that a few things. First of all, that if it's floating there quite happily, the net force is going to be zero. Right? If this cube is just, this grey cube is sitting here, we have a net force of zero. And if we have a net force of zero, then that means that the mass, the weight force of the displaced fluid has to be exactly equal to the weight force of the object. But remember, we don't have the same volume anymore. The volume is now different because the object is only partially submerged. When it was fully submerged, we had the same volume for both object and displaced fluid. When it's floating or only partially submerged, so they're the same terms essentially, then we have different volumes. So we can do some math. Follow along with this math. Make sure you can understand all the rearrangings. We're going from mass into density and volumes, cancelling out some gravities. And what we get is that the volume of displaced fluid is equal to the ratio of the densities. So that's the density of the object over the density of the fluid times the volume of the object. We just said that the density, displaced fluid volume is less than the object volume. Going back a slide, you can see that right here. The volume of fluid displaced has to be less than the volume of the object because there's part of this object poking up above the fluid surface. So if the volume of the displaced fluid is less than the volume of the object, then we have the density of the object over the density of the fluid is less than 1. So the density of the object is greater. No, I keep saying it the wrong way around. The density of the fluid is greater than the density of the object. All right, so rho O is less than rho F. The density of our object is less than the density of the fluid. And that becomes our rule for whether or not something floats. This works for any fluid and any object. You just need to compare their densities. And this may be something that you're already more familiar with. If you have something that's denser than water, it'll sink in water. Right? But now you can do it for any fluid by checking the densities. So as I just said, if the density of the object is less than the density of the fluid, it will float. If the density of the object is greater than the density of the fluid, it will sink. So that's a simple check for whether it will float or sink. If it's exactly the same, then technically it won't float or sink. It's very difficult for things to be exactly the same unless they are made of that fluid, but it does happen. And in that case, it won't accelerate up or down, but it may still be moved by currents in the fluid or other forces that are applied to the object. Of course, a classic example is a fish. A fish in water is the same density as water. Fish is made of a lot of water, and they end up being the same density. So they don't actually float or sink, but they can actually adjust their volume deliberately. They have little air sacs that they can inflate or deflate. Therefore, they can change their volume. And if they change their volume while keeping their mass constant, we know from density equations that their density is going to decrease and they will rise upwards within the fluid. So they can actually control their density to a certain extent and allow themselves to swim around quite happily. So the equation for the floating object that we saw, the displaced fluid volume is equal to that ratio of densities times the object volume. We can see that using that equation, if we know 3 of those variables, we can calculate the 4th one. So that's an equation we expect you to be able to use and manipulate and be able to determine one of those 4 if you're given the other 3. As an example, we're going to have a look at a floating iceberg. We've got a statement here that icebergs generally have a density of 917 kilograms per cubic meter. And we're also told that seawater, which has other stuff in it, so it's not the same density as pure water, has a density of 1030 kilograms per cubic meter. And we want to know what percentage of an iceberg will be below sea level. So as usual with these problems, I'll jump over to the document camera. Do have a go at it if you can figure it out, but we will work through it now regardless. Got our iceberg. Here's our iceberg. We've got the total volume of the object, right, is this. That's the volume of our object, whereas the volume of the fluid displaced is just this bit. Right, that's the volume of the displaced fluid. And we're asked for the ratio of them. So let's start by writing down the equation that we just saw. The volume of displaced fluid is equal to the density of the object over the density of the displaced fluid times the volume of the object. Now, because we've been asked for the ratio of these, actually just to reiterate that question, what percentage of an iceberg will be below sea level? That means we want DF, right? We want VDF as a percentage of VO, V object. That's what the question has asked us for. The percentage of iceberg below the surface. And if you remember how to calculate a percentage, right, what we need to do is go VDF divided by V0 times 100. That will give us our percentage. So we're looking for VDF over V0. And we've already got VDF and V0 in this equation, so let's just divide both sides by V0. And there's what we're looking for. VDF over V0, or VO, is equal to rho O over rho DF. So the ratio of the volumes is the same as the ratio of the densities. And so that's a useful thing to remember. The ratio of the volumes is equal to the ratio of the densities. So now let's put in our values. We were told that the density of the object, that's the iceberg itself, is 917 kilograms per cubic meter. And the density of the displaced fluid, which is seawater and is not 1,000, it's not fresh water, not pure water, is 1,030 kilograms per cubic meter. So if we just divide them, right, then that will be what we're looking for. So we get that VDF over V0 equals 917 over 1,030. And if you have your calculator and can do that equation, you will hopefully find out that we get 0.89. 0.89, but remember we need to times by 100 to get it into a percentage. At the moment it's a fraction, it's a ratio, and we want a percentage. So that becomes 89%. Right, so 89% of the iceberg is underwater. Now, icebergs might not always be exactly 917 kilograms per cubic meter, and the density of seawater does change. It varies by temperature and by the content of other things besides water and salt. So these two values can change, and if those change, then obviously our percentage will change. But in general, it will be somewhere around this figure. We will always have around about 90% of the iceberg below the surface. And obviously that's why icebergs can be dangerous, as we've all seen with Titanic and other movies, and just history in general. Icebergs are dangerous because there's so much ice underneath, and if they're not a predictable shape, they might have ice jutting out in places that we aren't expecting it. So we'll go back to the lecture slides. Continuing on, we have a review of all the stuff we've just looked at. So hydraulic lifts turn a small force into a big force. We looked at Archimedes' principle. Again, we derived that by working through thinking about a submerged object, and that arrived at Archimedes' principle, which is stating that the buoyant force is equal to the weight of fluid displaced. We defined apparent weight, and then we talked about floating. So whether the density of the object is greater or less than the density of the fluid will determine if it floats or sinks. And obviously introduced that equation relating the densities and the volumes. And so as usual, I'll stop this video here and I will do a separate one where I go through a few more problems for you. So do check that one out. As usual, try the problems first or during the video, but I'll see you there.